All right, so we're back recording. We're about halfway through class. You guys should get some good data. Now, walking around, looks like a lot of you guys, these numbers before and after, the momentum before and the momentum after, are pretty close to each other, which is ideally what this is supposed to show. So that's awesome if it is, right? Now, if there's a difference, if anything, the post-collision momentum might be a little bit less than the initial because the carts were slowing down because there's a little bit of friction. So that should make sense too, right? Now, if you were getting the post-collision momentum is about half of the pre-collision momentum, and some of you guys might be getting that. I can tell you exactly why that would be. Right. So I can put this on a graph. And so why would the momentum show up as half? Right, which not everybody got that, but some of you guys would have. Right, so why? Right, and that's if you were using stopping distance and stopping time to get your post-collision velocity, it would have worked out that way. Okay. So I'll call this graph post-collision velocity. Right? This could be a velocity versus time. Okay, some unit. Okay. Okay. So one cart is coming along, it's kind of bam, slam into the other one. Okay. Now, right at the moment that they collide, let's call that time zero. Bam, right there. So time zero. Okay. So we can get what's going on post collision. Right. So there's some v post, like a post collision velocity. Okay. Yes, if there was truly no friction, then what would this graph look like? If there was no friction? Yeah, you gotta say it just be a constant value, just be horizontal, right? That could like go on for like 100 miles like that, right? Right. But realistically, there was some friction. In fact, it was probably enough to stop the cart before the end of the track, maybe, right? So more realistically, what does this graph actually look like? Because here's the ideal value. Ideally, it would have been constant if there was no friction, right? But more realistically, it probably went to zero speed by the end. I'll call it T stop, like a stopping speed. Okay. Okay. Now, if you use the stopping time in conjunction with the stopping distance, I did so something like yeah, you guys know speed is distance over time, so you could use that, right? You guys know momentum is mass times velocity, right? So you can get this, plug it in there, and get the momentum. Right? No, but guys, if it's stopping distance and stopping time, but the velocity is always changing, what type of velocity is this actually solving for? Not initial velocity, not final velocity. How about an average type value, like an average type velocity? Because like the velocity is different at all different times post collision until it goes to zero. Okay, so this is like an average velocity. I'll call it like v bar, which is like an average. Okay, here's where that shows up on the graph. It shows up right here. So I'll call this v average, or how about v bar? It's the same thing. V bar and v average. Right. So now why is it half? Here's one way to think why it would be half. There's different ways to explain it, okay? But I can explain it this way: is area under the curve. You guys see this triangle-looking shape right here? Okay. Guys, that area represents what property of the lab you guys just did? Here's a hint. Look at the units. Meters per second. Seconds is an area something to do with base times height. And a triangle would be half that, of course. Okay. So if I have meters per second and I multiply it by seconds, what does that give you? Meters, which describes the distance. Okay, so that's how far the cart rolled. And if you divide that by the stopping time, that's what I'm saying right here, right? So the distance, which is the area of the triangle, divided by the stopping time, that gives the average velocity. That's like giving you average height. It's like taking the area of the shape divided by the base that gives you the average height, right? And here's sort of a way to think of that too. If you cap the times, so I'm going to keep this all constrained within the time interval. If this was a block of ice and the ice melts down to like a puddle of water, doesn't that water level go to like the halfway mark? Because it's a linear relationship here, so it'd be halfway there. Okay, and that's your average velocity, right? Okay. Now to bring this all together, guys, what is the true post-collision velocity compared to that average velocity that you would have calculated using this method? It's a factor of what? Yeah. So a factor of 2 to get back to the true post-collision velocity. So you could, if you did not account for that, then that's why your post-collision momentum would be half of your pre-collision momentum. Again, this wasn't true for everybody, but if you did this method, then I bet it would have worked out like that, because I've seen over the years that shows up like that over and over. Right? Another thing you could do is you could account for that. You say, okay, well, if I use this method, I know this is going on. So whatever velocity is in there for momentum again, I have to go ahead and double that to get the true post-collision momentum. And then it should restore these values, and then they actually would match. All right. So here's how we're going to finish this out. There is another lab on the other side. So here's the side you guys did today. On the other side, there's a different lab. Yeah, I've been walking around you guys' work. It looks good. You guys get some pretty good numbers. So I'm going to walk around one final check. If your numbers look good, I give you a turtle stamp. Hold on to that lab page. I'll give you guys some points in the book. You get a turtle stamp. And then we're do the other half another day. Another day. All right, that's a wrap on this recording and going into Thanksgiving.